So the key thing for C7 is understanding the difference between two types of reactions, and that is endothermic and what we call exothermic. So we're going to start with exothermic. Exothermic reactions imply the idea that only a small amount of energy is needed to break the bonds between the reactants, and much more energy is given off when forming the new bonds of products. And it's this excess energy which is transferred to the surroundings as thermal energy, increasing the temperature of those surroundings. So if we are dealing with an increase in temperature, that is an exothermic reaction. And then some key examples of exothermic reactions, we have respiration, neutralization, and the combustion of fossil fuels. They are all exothermic reactions. They all involve an increase of temperature. And we can draw exothermic reactions using what we call a reaction profile. On our y-axis is energy, and on our x-axis is the progress of the reaction. Please learn those. You may be asked to label them in the exam. Now, our reactants level is much higher than where our products goes, and this is because the difference between the reactants and the peak of the curve is what we call the activation energy. Now, that is the minimum amount of energy needed for reactant particles to collide and react. If we do not have enough energy to equal the activation energy, particles would just bounce off one another. Now, we know that there's only a small amount of energy needed to break the bonds between the reactants, so our activation energy is really small, it's really low. So that peak is essentially very close to the reactants, and most of our energy is released to the surroundings. So we have an arrow going down between the reactants and the products. The difference in the energy between the reactants and the products is equal to the amount of energy released and transferred to the surroundings as heat energy, thermal energy. And then we have the uses of exothermic reactions, and there's essentially two: hand warmers and food containers. We're going to start with hand warmers. Now, there are two types of hand warmers. The first one is disposable hand warmers. Now, this uses the oxidation of iron, so the reaction between iron and oxygen to make iron oxide, and it uses sodium chloride as a catalyst. Now, the advantage of disposable hand warmers is that they last for hours, but the disadvantage is that they can't be reused after they have already been used up. That means that they might be quite expensive and bad for the environment. The other type of hand warmer is reusable hand warmer, and this uses the reaction between sodium ethanoate and water. Essentially, the sodium ethanoate is dissolved into lots of hot water and then cooled down to crystallize, and those crystals are then activated and react with the water. Now, the advantage of reusable hand warmers is that they can be used multiple times, so they may be actually cheaper in the long run. However, the disadvantage is that they only last for 30 minutes, then they have to be returned to boiling water to redissolve the crystals. Food containers, on the other hand, use the reaction between calcium oxide and water. You essentially press a button on the base of the can, and that breaks the seal, allowing calcium oxide and water to mix. Now, the development of these food containers was really slow, and this was because it was incredibly costly. Much of the space was taken up by the reactants, and it was in too cold climates, food containers wouldn't heat up to a high enough temperature. And then we have our endothermic reactions. Now, in our endothermic reactions, more energy is needed to break the bonds between the reactants than the energy that is given off in forming the new bonds of the products. That therefore means that more energy is taken from the surroundings than is given back, and therefore we end up with a decrease in temperature. Examples of endothermic reactions include photosynthesis, the thermal decomposition of calcium carbonate into calcium oxide and carbon dioxide when it's heated strongly, but also the reaction between citric acid and sodium hydrogen carbonate. And that is because it's really easy to measure the decrease in temperature. In terms of our reaction profile then, our energy for our products is much higher than our energy from our reactants, and that's because we have a huge activation energy. Our curve is essentially going uphill. Our activation energy is between our reactants and the peak of the curve, and our energy taken in from the surroundings is the difference between, or the overall energy change is the difference between the products and the reactants. Uses of endothermic reactions then, ice packs. Ice packs use the reaction between ammonium nitrate, which absorbs energy, and water. Initially these reactants are kept separate, but then they are mixed together. These can be used in outdoor sporting events to decrease swelling as well as pain. They are disposable and they last for around 20 minutes. Another use of endothermic reactions is chilling drinks cans so that they can actually decrease the temperature of the surroundings to keep drinks like Coca-Cola cool. And you then have your required practical, which is investigating temperature changes in reacting solutions, essentially what we call calorimetry. Now, there are two things to know before we go into the experiment itself. First, we're going to conduct the entire experiment in a polystyrene cup. Polystyrene is a thermal insulator, and this will insulate both the sides and the bottom, enabling no heat to be transferred to the surroundings. As well, we're going to attach a lid which will reduce heat loss to the air. As for the actual experiment itself, step number 1, place a polystyrene cup into a large beaker. Step number 2, add 30 centimetres cubed of hydrochloric acid using a measuring cylinder. Step number 3, use a thermometer to measure and record the temperature. Then we're going to use a measuring cylinder to add 5 centimetres cubed of sodium hydroxide. Fit a lid and stir with the thermometer. When the reading stops changing, record the highest temperature, and we're then going to repeat, adding further 5 centimetres cubed of sodium hydroxide until a total of 40 centimetres cubed has been added. We're then going to repeat the entire experiment and find a mean for the maximum temperature for each volume of sodium hydroxide. We're then going to plot our results on a graph and draw a line of best fit, which should be a curve. The temperature will stop increasing after it's reached its maximum point, and this is because all the hydrochloric acid has reacted, but it will actually start to decrease, and this is because with increasing volume of sodium hydroxide solution, that our energy released is more spread out into a greater volume, and that will decrease the temperature. There are some safety concerns to be aware of. For a start, we are using glass equipment that can break and cause cuts. Therefore, if glass shatters, it needs to be cleared up by your teacher. Hydrochloric acid is corrosive and sodium hydroxide is an irritant. Therefore, if you get any of these liquids on your skin, you need to wash it off immediately. Just a few notes here. The bulb with the thermometer must be in the solution, and we stand the cup in the beaker to stop it falling over. Also, if you draw 2 straight lines through your points, one through the increase and one through the decrease, the point where they meet will provide you with the volume needed for the neutralisation for the maximum temperature. And the last mini topic is bond energy, which is the energy needed to break the bond between 2 atoms. It's measured in kilojoules per mole and is specific to the type of bond and the amount of those bonds. And you need to know that the overall energy change equals reactants take products. The energy needed to break the bonds between the reactants take the energy released when forming the products. And a positive value will mean an endothermic reaction and a negative value will mean an exothermic reaction. For example, if we had 2 lots of an H to H bond plus a O double bond making 2 lots of O to H, we are going to look at our reactants and products, so we can split the page. On our reactant side, we've got 2 lots of the H to H bond, so 2 times the value in our bond energy table, which is 432 for this specific bond. And then our O double bond is 1 lot of 495. We're now going to add those 2 values together, which will give us 1,359. On our product side, we have 2 lots of 2 O to H bonds, which means we've essentially got 4 lots of O to H bonds, so we've got 4 times 467, which gives us 1,868. We're then trying to calculate the overall energy change. That's reactants take products, so we're going to do reactants take products. 1,359 take 1,868 gives us negative 509 kilojoules per mole. Don't be alarmed, that is negative, that just means it's an exothermic reaction. And just some final notes then, it's always the temperature of the surroundings that increases. Energy that is transferred to the reaction is used up in breaking bonds. So if we're talking about a temperature increase or temperature decrease, you can assume that it's the temperature of the surroundings. And whenever chemical reactions take place, energy is always transferred. And this plays into the idea of energy conservation. Now, when the surroundings increase in temperature, that energy doesn't come from nowhere. And when the surroundings decrease in temperature, the energy doesn't just disappear. It's just being transferred between the reaction mixture and the surroundings. Energy is conserved within the system.